Thanks very much. So the topic here is not so much related to the Bootstrap, but it is related to many other fields in which quantum field theory is used. So that's one comment. And the other one is that if there is any question throughout, please stop me. It will be much more interesting, I think, if some questions are raised rather than me speaking without any interruptions. In particular, also this is not quite a colloquium. I'm trying some experimental presentation mode where I'll be actually solving a small problem on the slides. And so if there are any technical questions, it would be very much appreciated if you stop me. So quantum field theory, just as a general introduction, is of course a universal and very rigid mathematical structure that stems from the assumptions of quantum mechanics and from the theory of special theory of relativity. And it's a very rigid and omnipresent mathematical structure in many, many fields of physics. So it's, of course, the working horse in many different branches of physics, ranging from cosmology to elementary particle physics. On the way, of course, it touches very much on stochastic processes, condensed matter physics, and statistical physics, and so on. Now, many of the interesting open problems that still remain about quantum field theory, they have to do with strong coupling. So there are many, many situations in many body physics or in particle physics, and more generally in quantum field theory, where with the usual methods that we like to use and we learn in grad school and undergrad, such as linearized approximations and these kind of things, they don't work because of strong coupling. And these are just some famous examples where strong coupling is hindering progress in these fields. So what I would like to do here is to present some new ideas from topology, in which, in some cases, even strongly coupled systems can be tackled head-on, and one can extract concrete, precise results about interacting strongly coupled models. So this subject that I'm going to present has two facets. One is more mathematical, and I'll mention a little bit of the mathematical facet of that subject as we go. And the other one is the application to physics. And as far as the applications to physics are concerned, I'll be mostly discussing YangMills theory, even though most of the work I'm doing on the subject is more in 2+1 dimensions in the context of condensed matter physics. But I'll present an application from YangMills theory. So I'll start from an easy quantum mechanical model. So it's not going to be quantum field theory. There is a quantum mechanical model that exhibits essentially all the mathematical richness and physical ideas in this subject. It's a very nice pedagogical example that I learned about only a few weeks ago, or a few months ago, more precisely. And it appears in one of the papers on the subject. It's a very nice pedagogical example that encompasses a lot of the ideas that go behind this approach. And then I'll switch to more interesting examples by analogy. So I'll use the method of arguing by analogy to say that whatever we learn from this quantum mechanics is actually also true in YangMills theory, and it will have far-reaching applications for non-perturbative exact results in YangMills theory, solving a few long-standing problems about YangMills theory. In particular, proving some exact results about the vacuum structure of YangMills theory. So there are several papers on which this colloquium is based. One has already appeared with this gentleman, Davide Gauiotto, Anton Kapustin, and Nari Seiberg, and a few more papers are going to come out on related subjects. And I haven't mentioned all the collaborators, but this is just a few of the papers that are coming out or have already come out a few days ago. So let me start. So we'll start from just discussing a classical particle on a ring. A classical particle on a ring is a boring system. I mean, we have the angle q. Q is the angular variable, and we have some potential. So we just have a particle on a ring with some potential, and the potential is 2 pi periodic because it's a potential on a ring. And what do we do? For example, if the potential vanishes, then the solutions to these equations of motion are trivial. We just have particles going around the ring with some frequency omega, and that's the energy that these particles would carry. So it's a trivial system about which we know everything. The quantization of the system has already an interesting surprise. Even before you start, there is an interesting surprise in the quantization of the system that even though the classical system is unique and well-defined, the quantization is ambiguous. This doesn't always happen, but it happens in this system, that there is no unique quantization procedure. The quantization procedures are labeled by a 2π periodic parameter, theta, and it stems from the fact that the wave function doesn't have to be periodic. Unlike the potential, the wave function is not observable, and so it doesn't have to be periodic, and we can give it an arbitrary phase. The physical interpretation of this phase could be that you stick a tiny solenoid throughout the ring, so the ring doesn't see the solenoid, so it's like an Aharonov-Bohm phase. So this is my best attempt at drawing. I know that many of you could have done much better, but that's what I can do. So we have a particle on a ring, and we have a tiny solenoid. So classically, it would be invisible, but it affects the wave function. So that's one way to think about the system, that we have a solenoid stuck inside the ring with some magnetic flux phi, and this magnetic flux is nothing but the angle theta, which appeared here. It's the same thing. The best way to think about the system, in my opinion, is to actually imagine that the wave functions are periodic and implement this theta shift inside the Lagrangian. So the Lagrangian classically was just these two pieces, and quantum mechanically, there is a total derivative term that matters. So classically, this term would not matter because it's a total derivative, but quantum mechanically, it matters. And it exactly implements this effect that I've mentioned. How do we see that? We see that by Feynman's method of summing over histories. So some of the histories of the particle could involve going around the ring n times, and that would contribute a phase. So when you go around the ring, that would contribute a certain phase. So my convention is going to be that the wave functions are always going to be periodic, but there is this term that is going to affect the quantum physics, even though it doesn't affect the classical physics. So that's what I just said. This extra term affects the sum over histories because some histories go around the ring n times, and so you get a phase. So one has to, theta might affect the quantum physics, but not the classical physics. Now, in all of these presentations, it's obvious that theta is periodic. Theta and theta plus 2π are the same because they give the same phase in the Feynman sum over histories. Here, n is an integer, so theta and theta plus 2π are the same. So let's start quantizing the system. So far, it's a trivial graduate level exercise, but it will soon become much more interesting. But let me just review the quantization of the system, which is probably familiar to many of you from grad courses. Let's take a vanishing potential. For a vanishing potential, the theory is quadratic. And this funny term that we've added shifted the conjugate momentum by a constant. So the Hamiltonian is this, and pi q is just the conjugate momentum, so it's d over dq. What are the wave functions? You remember that we've insisted that the wave functions be periodic. So the wave functions are just e to the iqn, where n is an integer. And their energies are those. So you see that the energy spectrum depends on theta, unlike the classical system where theta did not appear. So this is the energy spectrum of the system. N is an integer, and theta is a constant, 2π periodic. An amusing fact about this energy spectrum is that it's not obviously 2π periodic. One has to do like a half fraction of a second manipulation in your brain to see that theta going to theta plus 2π leaves the spectrum of energies invariant, but it doesn't leave individual energy states invariant. You have to shift n by n plus 1. So theta going to theta plus 2π must be accompanied by taking the state n to n plus 1. So there is some sort of level crossing. Let me try. I try to draw it here. So if you change theta, this is what individual wave functions would do. So sometimes there would be level crossing. So this is like the wave function, let's say n equals, I don't know, 1. And this is the one n equals 0. And you see that they may cross as you vary theta, and they cross at exactly pi. So the only thing I need, and there are many more such parabolas. I just didn't draw all of them, of course. The only thing I would like you to remember is that there are two interesting values of theta that we would be discussing. One is theta equals 0, in which there is a unique ground state, and then there are excited states that come in pairs. So remember theta equals 0, a unique ground state, and excited states that come in pairs, because there are always two parabolas that intersect. The other interesting value is theta equals pi, where the ground state is twofold degenerate. That's exactly the point where two parabolas intersect. So there is level crossing at exactly theta equals pi. Okay, so the spectrum in total is invariant under shifting by 2 pi, but individual states you may need to do some level crossing. So you may need to change your branch and go down here. So do this kind of trajectory if you want to see the 2 pi periodicity of the energy spectrum. So quantum mechanically, you can establish rigorously the equivalence of theta and theta plus 2 pi by just finding a similarity transformation. So there is a simple similarity transformation that takes the state n to n plus 1. And that takes theta to theta plus 2 pi. So this is a unitary, well-defined operator on the ring that takes theta to theta plus 2 pi, and therefore the energy spectrum is the same. So theta equals pi is interesting because there is a qubit. So theta equals pi, the ground state is twofold degenerate, and it's a free system, and there is a qubit. It's interesting, but not earth-shattering. But for applications, you might imagine that having a qubit that is protected might be interesting. So we would like to understand the nature of this qubit. Why is it there? And if we do some perturbations, would it go away? So far, this was just the free quantum mechanics. It's very simple, and you don't need any sophisticated ideas to solve it. I just solved it for you. So now I'm going to make a claim which is very, very, very hard to prove by conventional methods. And the point would be that I'll show you some other methods which are powerful, stemming from topology, which allow to prove the following claim. And these methods turn out to be sufficiently powerful to also be relevant for interesting QFTs in higher dimensions. So the claim is going to be, suppose we had a potential on the ring. So a general potential could be decomposed into cosines and sines with integer frequencies. The claim is the following. Suppose you only have integer cosines with even frequencies. So k runs over the even numbers, even integers. So only C2k is non-vanishing. Then I claim that this qubit does not go away. So the claim is that the qubit that we saw at theta equals pi is robust under any perturbation which contains only even frequencies. Okay, this is already strongly interacting quantum mechanics. This is true for any coefficients, small or large. You could do some semi-classical computations when these coefficients are small using instanton methods, and you could try to check that this is true for the first few orders in your instanton expansion. But this is an exact result that is true for any coefficients, large or small. Okay, so I would like to show you some methods that allow to establish this result. This is a result about interacting quantum mechanics, so it's not as obvious as what I have presented so far. Are there any questions about the claim before I plunge into the proof? So just as a simple example, if you added a cosine potential on the ring, then the qubit would disappear. But if you added a cosine of 2q, then the claim is that the qubit will remain at theta equals pi. At theta which is not pi, there is no qubit and there is nothing to discuss. The ground state is unique and trivial. So let's study the free model again. So the way I'm going to solve it is that I'm going to study the free model from a new point of view. And studying it from this new point of view would explain why adding a potential of that sort doesn't perturb the ground state. So let's study the free model a little bit more carefully, talking about its symmetries and so on. So the free model, where you have no potential, has a rotation symmetry because the ring is homogeneous. So we obviously have an SO2 symmetry. SO2 just generates rotations along the ring. So that's an obvious symmetry. However, at theta equals 0 and pi, there is another symmetry, a reflection symmetry. This reflection symmetry is not obvious. Let me go back to that picture to explain it. So if there is no solenoid, it's obvious that there is a reflection symmetry. No solenoid is like theta equals 0, and the reflection symmetry is obvious. However, there is a reflection symmetry also when the flux here is a half integer, so it's pi. 2 pi is like 0, so pi is like a half integer. So if the flux is a half integer, there is still a reflection symmetry, because what the reflection symmetry does is to take the flux to minus itself, but a half and minus a half are the same, because the flux is defined modulo 1. Or in other words, theta equals pi and theta equals minus pi are the same, because theta is 2 pi periodic. So at both theta equals 0 and pi, and only at 0 and pi, there is this additional discrete symmetry of a reflection of the ring, because pi and minus pi are the same. So the full symmetry group at 0 and pi is O2, while the full symmetry group away from 0 and pi is just SO2. This is a subtle difference that would make what seems to be a subtle difference that would make a huge difference in the dynamics, that the symmetry is elevated or extended to O2 rather than SO2 at theta equals pi and 0. So let's try to understand the symmetry in a little bit more detail. We'll have to write the generators of the symmetry. So C would stand for the generator of reflections, and V alpha would stand for the generator of rotations by an angle alpha along the ring. So by definition, alpha is defined modulo 2 pi. It's just a rotation along the ring. So what do we expect? If you're just a group theorist and you want to write the relations for the group O2, these are the relations. 2 reflections are trivial. If you do 2 reflections, you get back to the unit. And if you do a reflection, rotation, reflection, you get a rotation by the opposite angle. So if you just do it on a piece of paper, you'll see it immediately that if you do a rotation, a reflection accompanied by a rotation, another reflection, it's like a rotation by the opposite angle. That's easy to verify. So what we need to do is to represent these operators on the Hilbert space. So we have our wave function c to the iqn, and this is how these operators act. And the action is different at theta equals 0 and theta equals pi. This is a crucial point. At theta equals 0, it's easy to guess how the action of these operators looks like on the Hilbert space. A rotation of the state n is it just gives you a phase according to the number n, e to the in alpha. And this reflection symmetry acting on n takes you to minus n. This is completely consistent with the spectrum. Let me show you why. So this is theta equals 0. So this symmetry C takes the red line to the yellow line, and you see that they are degenerate. So it commutes with the Hamiltonian at theta equals 0. However, this cannot be right at theta equals pi. This is where the physics starts, the interesting physics starts. This cannot be the right answer for how these operators act on the Hilbert space at theta equals pi. Why? Because n and minus n are not degenerate. So it cannot be possibly the right way to act on the Hilbert space because these 2 states are not degenerate. Indeed, if you look back at this formula, you see that at theta equals 0, n and minus n have the same energy, but at theta equals pi, they do not. So it cannot be right that this is the action on the Hilbert space. So in fact, the right action is that. So this symmetry of reflections accompanies n by a certain shift of 1 by 1. And you can check that this obeys c squared equals 1. So if you do it twice, you get back to yourself. If you do this procedure twice. V alpha acts in the same way. It's just a rotation of the wave function, of the coordinate q in the wave function. So this is where the interesting physics would come from this modification of the action on the Hilbert space. So let's do a sanity check and see if the group law is obeyed, because this is supposed to furnish the group O2. So at theta equals 0, we have to check whether this algebra CV alpha c equals v minus alpha is obeyed, whether this group relation is obeyed. So we write our action on the Hilbert space again. We just compute, and we see that this is perfectly OK. You can do it as a small homework exercise. This works. This relation works. However, at theta equals pi, we were forced into this action on the Hilbert space, and then we compute, and we find that it doesn't work. Okay, this is where the intricacies of this model start. That you thought that the symmetry is O2, and then you compute the group element, the group relations, and you have some phase, some funny phase. Okay? So the group relation is not obeyed. It's only obeyed up to a funny phase. It's interesting to observe that this funny phase is not an operator. It's a unit operator. It's like a C number, but it obstructs the group relation in some way. So the way this is called is a central extension. So the quantum mechanical model does not have an O2 symmetry. It has a central extension of O2. And this is called central because it's not an operator. It's just a C number. It's a phase that acts in the same way on the full Hilbert space. So mathematically, you could say that the projective Hilbert space is a representation of O2, but the full Hilbert space is not. The full Hilbert space is in a certain representation of a central extension of O2. If you learned ever about two-dimensional conformal filters, there's a central extension, which is the central charge, which is very common in CFT, in discussions of CFT in 2 dimensions. This is the same thing, just in quantum mechanics. This is a central charge in quantum mechanics. So let's do the analysis a little bit more carefully now. So we found this weird modification of the O2 group relations. And the first question you might want to ask is, can we get rid of it? Is it really necessary? Can we get rid of it by some change of variables, rephasing what we call the wave functions, or redefining what we call the charges? So you try to get rid of it. For example, you could try to define U alpha, which is related to V alpha in this way. And indeed, you almost managed to get rid of it, except that now alpha is not valued in 2 pi, but in 4 pi. Because you had to multiply by e to the I alpha over 2, which is not 2 pi periodic. You see that you almost managed to get rid of it, but not quite. There is a certain Z2 that you did not manage to get rid of it. And so mathematically, what we would say is that the Hilbert space is not in a representation of O2, but in a double cover of O2, which mathematicians call pin 2. So the actual symmetry is pin 2 rather than O2. And we'll see what's the physical meaning of that in a second. This is very similar to how SU2 is related to SO3. It's the double cover. Now, when you make this analogy between SO3 and SU2, you think about spin. So you should think about the same here. This extension of O2 to pin 2 has the following physical interpretation, that in fact, the particle on a ring, when the flux is exactly a half integer, is not a boson, it's a fermion. So when we take it around the ring, it goes to minus itself. That's how you could interpret this fact that alpha is not 2 pi periodic, but only 4 pi periodic. So you need to go twice around the ring to go back to yourself. So you can think about it as a sort of a fermion. So we can think about the particle Q of t as a fermion. So in fact, it's mathematically true that if you just quantize a free fermion, it has 2 symmetries. One is charge conjugation, where the fermion goes to fermion dagger, and it has phasings. You can add a phase to the fermion. These two symmetries together comprise an O2, but the O2 again has a central extension to pin 2. So mathematically, these models have exactly the same properties, that the projective Hilbert space is in O2 representations, while the full Hilbert space is in a P2 representation. So these models are dual. So a particle on a ring with a half integer flux is exactly the same as a free fermion. It has the exact same symmetries, the exact same central extension, and the exact same ground state. So this is an example of, if you want, boson-fermion duality, that bosons and fermions can be the same in quantum mechanics. This is the simplest model of this sort. So what we're doing here is that we're dealing with a system which we can now introduce the word anomaly. When this happens, we can say that the system has an anomaly. When the symmetry does not techno the Hilbert space, we could say that the symmetry has an anomaly. More precisely, it's a 't Hooft anomaly, not to be confused with something else that's called ABJ anomaly. The model has a 't Hooft Z2 anomaly. That's just a name. And the main point here is that while we had this O2 symmetry, it's not really necessary for the physics, for the physics of this group extension to be in place. In fact, it's efficient to preserve a subgroup of the rotation symmetry of the ring. So let me explain that. Suppose you added some impurities on the ring, or you added some potential on the ring. Since we have a central extension here by Z2, Z2s cannot disappear. Z2 is like either -1 or 0. So you cannot continuously make a -1 disappear. Mathematically, the way you say that is that suppose we preserve the Z2 times Z2 symmetry inside O2. So we had reflections, but rotations by 180 degrees would be, and only rotations by 180 degrees. So suppose the ring was deformed by impurities or a potential in such a way that only 2 symmetries out of this O2 group would remain. One is reflections, and the other is rotations by 180 degrees. So we would have 2 generators out of these generators that we've previously discussed. One is rotations by 180 degrees, and the other is reflections. And they would satisfy this group law. Classically, there won't be a central extension eta, but at eta equals pi, eta is -1. So this -1 that we saw, the central extension, does not go away even if we just preserve a Z2 times Z2 symmetry. And therefore, any perturbation of the system that preserves Z2 times Z2 symmetry cannot make eta disappear, because eta is -1. And therefore, the degeneracy in the ground state must remain for arbitrary perturbations that preserve Z2 times Z2. In fact, this group is called the dihedral group of it's just the symmetry of a square. So while classically the system only seemed to have Z2 times Z2, quantum mechanically there is a central extension, and the symmetry is the dihedral group with 8 elements. And you can think about it geometrically, like you have a qubit, your famous qubit that is the ground state. And you can think about it as like the sides of a square. It sits in a representation of the dihedral group that looks like the sides of a square. And therefore, it cannot go away because of the central extension. And therefore, you conclude that as long as you add only potentials or impurities that preserve Z2 times Z2, the qubit cannot go away because the central extension cannot go away. Now, from the point of view of just general folklore in quantum mechanics, this is extremely surprising because we see a system here with a potential. It's not free, and yet it has exactly two degenerate ground states. This is very weird from the point of view of quantum mechanics because we're told that instantons always leave the degeneracy in quantum mechanics. So everybody who studies quantum mechanics goes through the example of a potential with two minima. And classically, there are two degenerate ground states. But quantum mechanically, the symmetric combination is the true ground state while this anti-symmetric representation is lifted. So how come we found a system where two ground states are exactly degenerate? So classically, when we have a potential that looks like a cosine of 2q, there are two ground states, but quantum mechanically, they should have been lifted, exactly like in the example that everybody studies in school. So what happened here? The point is that this example is extremely misleading. This example that we go through in grad school is extremely misleading because it only has a Z2 symmetry. And the group Z2 is special in that it doesn't have central extensions. So central extensions are measured by a group cohomology, and the group cohomology of Z2 vanishes. So Z2 just doesn't have this potential of having a central extension. And from this point of view, it's extremely misleading. Any system with at least Z2 times Z2 symmetry can potentially have a central extension, as I've demonstrated with this particular example of a particle in a ring. And this central extension is by a Z2, and then the ground state cannot be lifted. So it seems that this phenomenon that the ground state is unique and symmetric that we learned about in grad school is actually not the rule, it's an exception. This case is an exception. Most groups have non-trivial central extensions. And then when you construct systems, quantum mechanical systems with those symmetries, it's possible and generic that central extensions would exist. And then the ground state cannot be unique. Okay, so the lesson here is that as long as there are anomalies, the ground state cannot be trivial because there is a central extension, so the ground state cannot be in a singlet representation. And this is very similar to arguments that if you've ever seen arguments based on a 't Hooft anomaly matching, this is very similar. This is like a quantum mechanics version of a 't Hooft anomaly. We have a Z2 anomaly, and we match it in the ground state by requiring that the ground state is twofold degenerate. And these kind of anomalies appear to be extremely common. Such discrete anomalies appear to be extremely common, not just in quantum mechanics, but also in quantum field theory, as you'll see. Unlike the usual discussion of anomalies in quantum field theory, which requires fermions and even dimensions, and it doesn't appear in quantum mechanics, this type of phenomenon seems to be very, very common. And it does not require neither fermions nor even dimensions. So now I'm going to use what we learned from this model to discuss YangMills theory. And I'll claim that YangMills theory has the exact same phenomenon. And I'll use that to prove an exact result about the vacuum structure of YangMills theory. So are there any questions about the quantum mechanics model before I switch to the other subject? Any questions? Oh, yeah.
Can you find an example that has this degeneracy preserved, but there's no theta angle? There's just a potential.
So the question is whether these theta angles are necessary. The theta angle, I mean, abstractly speaking, any system that has a Z2 times Z2 symmetry, which is quantum mechanical, can have such central extensions. Now, how you choose to realize it using a microscopic Lagrangian is up to you. I've just presented this example because it's analogous to YangMills theory. But I can give you other examples which at first sight don't have theta angles, but there may be another description where they would. It's a question of like how you choose to formulate the theory. The formulation independent statement is that any system with Z2 times Z2 may have a Z2 central extension. And so every time you have such a system, you have to check. Now, you can you can try to prove that some class of models, let's say models made out of bosons only, and some potential, unless they have a theta angle, there won't be a central extension. You could prove such a theorem, maybe. Yeah. So you could prove that some class of systems does not have this phenomenon. But for example, if you study free fermions, this appears. If you study bosons with theta angles, it may appear. And so it's hard to say when it does and when it does not. The only way I know how to check it is case by case. I don't have general theorems about when it does or it does not appear. Yep. Any other questions about this part? OK. So now I'm switching to YangMills theory. Now, a discussion of YangMills theory would not be very pedagogical. I mean, not nearly as pedagogical as the discussion about quantum mechanics, for the obvious reason that I can't teach you YangMills theory. But I'll just present analogies, and maybe the analogies would be appealing enough. So I'm just reviewing notation. It's not supposed to be a course on YangMills theory. I'm just going to review the notation. YangMills theory is just a nonlinear version of Maxwell's theory. And if you don't know these equations, the only thing you would actually need to know for what I'm going to say is that the difference between YangMills theory and Maxwell's theory is that the electric fields and magnetic fields in YangMills carry themselves charge. So the electric and magnetic fields are themselves charged under the YangMills equations. So the theory is nonlinear. And that's the only thing you would need to know. So now I would like to discuss a crucial difference between YangMills theory and Maxwell's theory. And this crucial difference would be very, very important for the statement that I'm going to make about the vacuum structure. The crucial difference is that when we study Maxwell's theory, we often consider probe charges. And we study the electric fields and magnetic fields the probe charges induce. And the way we are taught to measure the electric charge inside some region in space is just to measure the electric flux, right? We just measure the electric flux through some sphere, and that counts exactly how many charges we've inserted. We can ask if there is an analog of that procedure, namely the Gauss law, also for the YangMills fields. The YangMills fields are nonlinear, so it's not as obvious as the usual Maxwell's equations, whether there is such a Gauss law or not. So we're going to have now a serious discussion about whether there is or there is not an analog of Gauss's law for YangMills theory. So let's have this discussion. It's going to be very qualitative, but the physical idea here is that the reason that in Maxwell's theory Gauss's law works is that if you insert a charge, it creates some electric fields. But electric fields don't have charges themselves, so you can measure the electric flux and you don't get confused. However, in YangMills theory, when you insert a charge, it creates some nonlinear YangMills fields, but the YangMills fields carry charge themselves. So if you try to measure how much charge there is inside some sphere, you may get confused because the YangMills fields themselves carry charge. But it's not, you don't have to give up, because the point is that the YangMills fields carry charge in the adjoint representation of SUN. So in some loose sense, it's like they carry charge n, or not 1, where n is the SUN. So if you insert some charge, you may get confused because of the YangMills fields, but you would not, but the information would not completely disappear, because the YangMills fields only have charge n. So suppose you inserted charge 2, so you might measure 2 plus n, but you know that the 2 is right. So you will be able to measure the charge correctly modulo n. And so we have a Zn. So that's when people say that YangMills theory has a Zn center symmetry. That's how it's technically called. That's what they mean. That in YangMills theory, you can measure the charge modulo n, because the YangMills fields have charges in units of n in some convention. In Maxwell's theory, if you want to be pedantic, you could say that the center symmetry is not Zn, but it's SO2. So you can measure any integer charge you want. So this is point number 1. And you will see that this Zn is very, very important. The second point is that similarly to this particle on a ring, when you try to quantize the YangMills fields, you can start from the classical equations and quantize them, but there is an ambiguity, which is very, very similar to the ambiguity in quantizing a particle on a ring. In YangMills theory, we can also add a theta angle, which multiplies trace f wedge f. So this is perfectly analogous to q dot. You may not know what this means or so on, but this is perfectly analogous to that. It's the same physical phenomenon, that the space of configurations has a non-trivial cycle, and we can add a theta angle according to that. So the quantum theory depends on theta, very much like the quantum theory of a particle on a ring dependent on theta. And very much like in the case of the particle on the ring, theta is 2 pi periodic. So YangMills theory is not unique. When we quantize it, we have a theta parameter, and this theta parameter is 2 pi periodic. So this, so far, it's very analogous to the particle on the ring. Another analogy is that 0 and pi are special. In the particle on the ring, in those cases, you had an O2 symmetry rather than SO2. In YangMills theory, at theta equals pi and 0, we have time reversal invariance. Sometimes we can think about it as CP, charge conjugation accompanied by parity, but you can also think about it as time reversal. So in these two choices of theta, there is an additional Z2 symmetry, like in the particle in the ring. It's time reversal symmetry. And again, you can prove that theta is 2 pi periodic by doing a similarity transformation. So the last remaining piece of the puzzle is what is the analog of SO2. We saw that there is the analog of reflections is time reversal. The analog of SO2 for the particle in the ring is our Zn. This part is a jump. It's a logical jump that I'm not going to be able to explain. But mathematically, the center symmetry in YangMills theory plays the same role as rotations on this ring. So the Zn is a discrete analog of SO2. This is the only point that I don't know how to explain by an analogy. It's just a jump. You just have to accept the fact that mathematically Zn and SO2 are similar. So the last piece of this analogy between the quantum mechanical model and YangMills theory is that there is an anomaly, a central extension. So what we claim is that at theta equals pi, these two symmetries, time reversal and Zn, have a mixed anomaly. So this is an anomaly in YangMills theory, which has no fermions. It's just a theory of bosons. And it has a discrete anomaly in 3+1 dimensions. So it's a 3+1 dimensional QFT with a 't Hooft anomaly in spite of the fact that it does not have any fermions. It's not chiral. There is still a discrete anomaly. And for the same arguments as in the quantum mechanical model, if you have a discrete anomaly, you cannot have a trivial ground state. So we claim that time reversal symmetry is spontaneously broken in YangMills theory at theta equals pi. There are 2 degenerate ground states. This is our qubit. In the quantum mechanical model, this was a qubit. So these there are 2 degenerate ground states. And you can ask a funny, an interesting physical question. What happens if you try to interpolate between these 2 ground states? Unlike in quantum mechanics, we have space. So we can try to interpolate between one ground state and another. And I'm just going to mention that for the people in the audience who are interested in quantum Hall and 3D systems. It turns out that when you try to interpolate between these 2 ground states, the theory that lives on the domain wall that separates one vacuum from another is an SUN level 1 Chern-Simons theory. That follows from the anomalies uniquely, almost uniquely. It follows from this anomaly business almost uniquely. This observation is actually the starting point of many exact results about 3D systems from 4D systems that are in preparation. So one can discover new 3D dualities and prove previous suggestions for 3D dualities by using the fact that YangMills theory can reproduce interesting quantum Hall states on domain walls. Let me also mention some applications of this fact that time reversal symmetry is broken for finite temperature. So at finite temperature, generally speaking, we intuitively expect that symmetries would be restored. So the idea is that if you heat up YangMills theory sufficiently, time reversal symmetry would be restored. And you can ask, at what temperature is the time reversal symmetry restored? It may be restored before the gluons get deconfined or after the gluons get deconfined. So as you heat up YangMills theory, 2 things happen. One is time reversal symmetry needs to be restored. And the other thing is that the gluons may liberate. So they are no longer confined inside hadrons or globules. So the anomaly implies, in fact, since the ground state cannot be trivial, that it cannot happen before. It must happen only after. So this is a very precise inequality that you can predict for the phase diagram of YangMills theory just from this Z2 anomaly. If it were to happen before, there would be an intermediate phase where the quarks are confined and time reversal is unbroken. That would contradict the fact that the ground state cannot be trivial. So it must only happen after. And there is a further prediction that it ends at the 2nd order transition, which is in the 3-dimensional Ising model universality class, which is a model which is very, very familiar to people who study CFTs in 3 dimensions, and especially Bootstrap people. So this is supposed to be the universality class of this endpoint here. Let me also make some comments about phenomenology. So first of all, in QCD, of course, there are quarks. And so once you have dynamical quarks, this Zn center symmetry, which allows you to measure charge mod n, disappears. So there is no Zn symmetry in real life QCD because there are dynamical quarks. But it turns out that you don't need this Zn. This is another elaboration that I can't explain. It turns out that having the degenerate quarks is enough to have this kind of Z2 anomaly. And so the question of whether this happens in real life or not is of actual interest in QCD or variations of QCD, gauge theories with quarks. If some of the quarks have negative mass, negative sign for their mass, it may actually be that this is the correct phase of QCD. So you can actually prove that if one of the signs is negative and if the quarks are degenerate, time reversals must be spontaneously broken in QCD. And this can also drive the breaking of CP that we know exists in the standard model. So this could be a mechanism that could generate CP breaking. Now, I only presented here one example of this Hooft anomaly business and how to prove non-perturbative results about strongly coupled QFTs and quantum mechanics. Here, I'm going just to list a few other examples. The first I already mentioned. It turns out that the center symmetry is not necessary. There is an anomaly even if the quarks are exactly degenerate. And this is also what gives rise to this interesting connection to quantum Hall states and 3D dualities and 3D Chern-Simons theory. Yep?
Negative mass or negative mass squared?
The quarks are fermions, so their mass is a complex parameter. And it makes a huge difference whether this complex parameter is real negative or real positive. The sign of the quark mass is extremely important. The mass squared is always positive. But the mass in the Lagrangian is in the complex parameter. You can rotate it, and then it would be compensated by adding a theta term. So a nice convention to pick is that there is no theta term, and then the sign matters. And that's what I meant. Thanks for the question. So the first other example is QCD. The second example is quantum antiferromagnets, which are very closely related to Bootstrap and CFTs. And that's what I'm actually going to discuss today after the colloquium in this lecture that Pedro mentioned. I'm going to discuss the Neal VBS transition, which is a certain transition beyond Landau-Ginzburg. And it's completely powered by a Z2 anomaly. So I'll explain how a Z2 anomaly gives rise to this story. Chern-Simons theories appear naturally to have discrete anomalies. And there are many constructions involving abelian Higgs models that are similar to the Haldane chain, and many, many others. So the phenomenon of having such discrete anomalies that allow you to prove exact results about finite temperature or zero temperature, quantum phase transitions, non-trivial ground states seems to be extremely common. There are many, many examples where this can be used. These ideas can be used. So in all of these cases, one can make strong non-perturbative claims about the ground state, not relying on lattice, Monte Carlo. It's just an exact claim that is powered by the topology of the field space. And today I'll present another such example, which is very interesting. So topology offers a window into non-perturbative physics. And it leads to concrete results. It's not just like some vague notion that something must be going on. It leads to concrete inequalities, concrete results about the number of ground states, concrete results about domain walls, and so on. I mean, as I've emphasized many times, you don't have to have fermions. It doesn't have to be chiral. It can have perfectly vector-like bosonic theories, and even in quantum mechanics. Now, the mathematical underpinnings of these developments, I just hinted that group cohomology is involved. I just discussed H2. But this business with projective representations and H2 is the mathematical underpinning of these things in quantum mechanics. If you want to understand, for example, the mathematical framework that you need to understand anomalies in Yang-Mills theory, it's more advanced. You need to learn a little bit of discrete characters theory and algebraic topology, and even higher gauge theory. So these are actually tied to modern mathematical developments. And the applications are for dualities in 3 dimensions and ground states of Yang-Mills theory, and so on and so forth. Oh, I forgot to put the last thank you slide. Thanks so much.
Time for questions. For the case of YangMills that you presented, there are other ways of realizing a non-trivial vacuum, right? Besides breaking time reversal.
Yeah, so in YangMills theory with fermions, with fundamental quarks, you could have massless fundamental quarks, and then there would be a chiral Lagrangian massless pions. That's also a non-trivial ground state. And this was explained in the 70s to be associated to a continuous 't Hooft anomaly. So this is a standard 't Hooft anomaly involving the axial and vector symmetries. That's a well-known story. The surprise here is that there is a variant of that story without quarks, and it's a discrete variant, but it still predicts the existence of two degenerate ground states and time reversal symmetry breaking, or if you want CP breaking, it's equivalent. So it's like, it's a discrete version of what people have studied in the 80s. But it hasn't been appreciated. People didn't know that such things exist until a few weeks ago or months ago. And also the mathematical framework to describe these discrete anomalies has not existed in the past.
But is it clear that time reversal needs to break for any value of n?
Oh, that's a fantastic question. Okay. Yeah, that's a fantastic question. So this system has a mixed anomaly between time reversal and Zn. So mathematically speaking, there are two possible ways out. One is to break Zn, the other is to break time reversal. If you break Zn, Zn is a center symmetry. What it means is that the theory deconfines. So quarks, even at zero temperature, would be deconfined. This sounds a little bit implausible, but it's extremely hard to rule out. And for sufficiently small n, such especially n equals 2, it's a possibility that should be explored. And it has some initial explorations in that direction have started. Since there is an anomaly, it's a logical possibility. It should be explored. And the consequences are quite dramatic if you have a zero temperature deconfinement of quarks. It changes the phase diagram very, very dramatically. So this phase diagram was drawn with the premise that it's the other scenario that happens, that it's time reversal that breaks. So you can try to investigate what happens to this phase diagram if Zn was broken instead. And you find that you need a few new critical points, and a few new exotic critical points in 4 dimensions at zero temperature. It's quite interesting. And indeed, I don't know how to rule it out. It could be that for SU2, YangMills theory, that's what happens. But for sufficiently large but finite n, one can make a strong argument based on large n counting that this is disfavored, that this phase, one can make an argument based on large n counting that at sufficiently large but finite n, this is disfavored, and it's rather break time reversal symmetry. And if you look at ADS-CFT constructions of YangMills-like theories, that's what happens. Time reversal symmetry breaks spontaneously. So yeah, when I drew this phase diagram, I should have been more precise, but it's a colloquium. I should have said that. I even said it here. I put it in parentheses. This.
Oh, I didn't see that.
I should have been more precise and say that this is probably the right phase diagram, starting from 3. But for n equals 2, it might be that there is a deconfined critical point here. It could be tested on the lattice in the future.
More questions? So we heard a seminar a few weeks ago with David Tong who said that we don't really know what the global symmetries of QCD are. We may divide by these discrete symmetries. So how would that, do you have an experiment to check if we have these discrete symmetries or not?
Yeah, that's I don't know what David said, but what he meant to say was that we don't know what the gauge group of the standard model is, not what the symmetries are. The gauge group of the standard model could be SU3 times SU2 times U1, mod Z6, or it could be mod Z3 or mod Z2, or it could be mod nothing. We just don't know what's the right gauge group. Now, depending on the choice of the gauge group, the symmetries change. So the center symmetries depend on what you divide by when you define the gauge group. And for some choices, there might be an anomaly of this sort, and for some choices, there might not be an anomaly. And there is an interesting question of how do we fix the gauge group of the standard model. This discussion is a little bit tangential to what I was talking about. I was talking about pure SUN YangMills theory, which can be put on the lattice, and these predictions can be checked. The question of what is the exact gauge group of the standard model is slightly tangential, but it's an interesting question. And I didn't think about how to, I didn't think if there is a nice low energy experiment that could test these discrete subgroups that we may or may not need to divide by. Unification, however, strongly suggests that we need to divide by Z6. So if you're a believer in SO10 or SU5 unification, then this is forced on you.
More questions?
In your Quantizing pi example, you're connecting vacua with the same topological charge?
Here?
Yes.
Yeah, so the idea here is that since it's not quantum mechanics, we have now space, right? So it can be that in one part of space you're in one ground state, in another part of space you're in another ground state. And then in the middle something has to happen. You can ask if the topological charge is the same. And I don't exactly know what you mean by topological charge. Do you mean the winding number? The winding number is not a charge. So I don't exactly know what you mean, but there is a slight variation of what you may, which is correct, which is the contact term. So these two vacua have a different contact term for background. So ZN symmetry, like any symmetry, can be coupled to classical sources, like classical gauge fields or chemical potentials, if you want. So these two vacua have different, if you want, different contact terms for these background gauge fields. So you could say that they have different topological charges. If you want to be sophisticated, you could say they support, one of the vacua supports a Digraph-Witten theory for higher gauge theory, Digraph-Witten theory, and the other does not. But basically, you're right. These two vacua are distinguished by some topological term. And that's why when you interpolate from one to another, what happens in between cannot be trivial, because it needs to introduce a certain jump in some topological term. And that's why you need the Chern-Simons theory. The Chern-Simons theory implements a certain quick jump from one contact term to another contact term. That's how you essentially prove that you need to have this thing in the middle.
In the case of θ equals 0, you have only one.
That's what everybody believes. That's what the Clay prize is for, that you have one gapped massive ground state. But we proved that.
If you have θ different from 0, pi. I mean, in terms of number of particles.
What we proved is that at equals pi, this cannot be true. There must be two ground states. What happens in between is probably there is one. If you believe this phase diagram is based on the premise that there is one ground state here, 1, 1, 1, 1, then there are two, and then again 1. So it's like a first order transition at 0 temperature. It's a quantum phase transition because it's at 0 temperature, and it's first order. So there is like one ground state here, one ground state here, and they just cross. So this picture is a sort of this picture is sort of a generalization of this picture, where you have one ground state on each side, but here you have exactly two. You see what I'm trying? So it's like a first order transition at 0 temperature. That's what we claim happens in YangMills theory.
Yeah, there.
Sorry, just one question.
1 second. The mic is there, so that we can record.
Just one question. It was concerning this central extension you called for SO2. I remember something that
For O2. For O2, the central extension was for O2. O2. For SO2, there are no central extensions. That's why it's important that it's enhanced to O2.
Because I remember something like that simple group, they don't have central.
Exactly. That's exactly what I said. So the point is that as I said here, at θ equals 0 and pi, the group is extended to O2, not SO2. And that's why at θ equals 0 and pi, you may have a central extension, which takes place at pi, but not at 0. So it's really important that it's O2, not SO2, because SO2 does not have non-trivial central extensions.